All right, let's do question 11 here. So the subgraph of a G is the graph with where its vertices are like subset of this vertices of this graph, and the edges also the subset of the set of the original set of the edges in the original graph. All right. So I hope you understood what I said. And the spanning subgraph is the special case of the subgraph such that it covers all the vertices of the original graph's vertices. And if that spanning subgraph is also tree, we will just call it spanning tree. All right, so you got A, B, C, D. So a complex graph is 4 vertices. So I will this one, and for each of these, specify that whether it's subgraph. Okay, so G prime part A is this guy, A, B, C. So this guy. So it's just nothing. Yes, it's subgraph. And part C, I jumped part B because I know that you can do that by yourself. So A, B, C, D. What else does it have? A, B, B, C for sure. C, D, and the A is the subgraph, and it's a spanning one. Spanning subgraph, and it's not tree. All right, and you can see that part D. Can I write that like this? A, B, A, C, and A, D. It's spanning tree. All right, let's do this question now. So we see this one, a depth first search DFS algorithm to find the spanning tree of a graph works as follows. Label the vertices, all right, so which has been labeled here. Consider graph G1 defined by the diagram below. Use alphabetical order and first search to find a spanning tree for G1. So spanning tree. So we want to find a subgraph from this one, which is a spanning tree for this graph. So we will label all of the vertices which have been labeled already. We will list vertices in some order. What's our order here? It's alphabetical order. All right. And take the first vertex A. So okay, so A is the vertex root. Okay, and take the vertices in the order by they are given and join the vertices and their edges one at a time. So I got this B. So I've got D here. So A was here. I chose B and D. So I just followed this one, taking the vertices in the order they are given. I joined it to the vertices. Okay. All right. So take the first vertex as a root, which is this one, which is a root, and the edges. Okay. I got the edge. Okay. One at a time, each vertex added to adjoining to the most recently used vertex. If so, this will be continued. Or so if not possible to adjoin a vertex to the last used vertex, backtrack only as far as necessary to reach a vertex where you are able to add another edge. All right, so we will repeat until we will cover all of the vertices, and it will be a tree. So I've got B, D as the left and right children, respectively. So now here is the thing. B. What's B in it? So I just follow this one here. B. B has got E, F. All right. So I can, so since E is not not connected to the D, so I will include it here. So this will be D, and there will be F here for sure. Now here's the thing. So G is not connected to not this one and also not this one. So I have to adjoint it to the B here, G. And how about this one? C comes first and H not have any other option. So C, H. Okay. So we can do the same job for the reversed alphabetical order. So if I list them, it will be H. What's the order? Actually, I can do this. A, B, C, D, E, F. Can I make this for G and H? Okay. So all right. So this one, this reverse. So I will put H here for sure. There's no other option, so I need to do this one. C. So I didn't like do this. I didn't do this because I have just one option. Okay. C. Again, it's the same thing. F. And now from F, I have B and D. So F, I will put B here. Okay. From B, I can have B and D, I think. Yeah. Let's proceed. If it's mistake, I will come back. And so from B, I have A. Okay. And now from A, I have G. I have, so I put this one here. I will have A. So this will be E also here. And there will be a G here. Okay. So anyway, I can put actually I can modify this one. Let's move this one here. Part A, part A. For part B, I can do this H, C, F, again, another one B, all right? So this will be, so taking the vertices in order that they are given, adjoint the vertices and their edge. So B, so from here, we can have, if you look at this one, so I have A, I have E, okay, so I can have A, I can have E, right? And need to modify this one. I don't modify this one, A, and from A I have G, or I have D, sorry, I have D, and I have G. Here I can, so as I said, BA, this will be G. Can be like this as well. But I'll ask this one, probably this one is, this is the right one. Okay, so binary breeds first search algorithm to find spanning tree of a graph. Okay, works as follows. So again, we will have this guy here. So I can do this one, alphabetical order, alphabetical order. So we will label the vertices, which is A, B, C, until H. And so we listed that. Take the first vertex as A as a root. Take the vertices in order given adjoint as many as possible to the root. Okay, so it will be just how many of them? So let's do this one. Okay. So A, B, so 3 of them. B, B, G. Okay. So now we proceed the first vertex on level 1. Okay. First vertex B, D, G. Okay. And adjoint as many as the remaining vertices of G as possible to it. So what do we have? B. So we've got E and F. So I will sign this one, this one. E and F. So first vertex of level 1. So we did it. So we can see for D and G now because for the other level 1. So for the other level 1, D is just So it doesn't have anything to adjoin to this tree. And about the G, it doesn't have as well because we already used E. Therefore, I will go to the level 1, E and F. E is just poor, F has got C, and it will be like C, like H. This is part A. For part B, so it will be H, G, until A. So I will write H here, okay? And I will look at this one here. So then I will choose C, then I will choose F. So this will be C, this will be F, and you can continue for sure. This one, it's okay. A minimal spanning tree, MST, is spanning tree of it graph with minimum possible weight out of the span. So let's do at least one of them here. Okay, so I see that the original graph is G, A, B, then C here, then C, D, then D, A. Okay, so A, B, the weight of this one is 1, 2, 3, 4. So minimal tree MST is the spanning one. So actually, yeah, it's obviously we will do like this or this one, or we have to do this one. So, or we can do this one. So obviously we can just not consider this one. So the minimal one will be this one. So it will be the minimal spanning tree. Okay, so you can do this question as well. This question 15 here, and this was question 14. Okay, so question 15 for you. Okay, now about this interesting algorithm. All right, so what do we do here is this. So I will choose Madrid. So I will choose here. All right, so I will follow the algorithm to start with. So I want to choose, I want to find the minimal spanning tree. So the goal is to find a minimal spanning tree. So let's remind you that a minimal spanning tree is just a subgraph covering all the vertices of the original graph, and it's a tree. Okay, the graph is weighted, so we will choose in a way that the graph will be, the summation of the weights all will be minimal. Now, here's the thing. So I choose the T will be a future tree, minimal spanning tree. So I will choose a vertex here, Madrid, any of them. You can choose any of them. In any case, because you have to cover everything. So I will call this one S, and I will choose the one that least weight. So 6, 5, 15, 25. So I will choose definitely this one. So I will go here. All right. Now S or T. So again, from this one is, I will call this one T because according to the second step. Then I will again follow the third one. Okay, so 7, 16, and also for this one S, this one was T. 6, 15, 25. So I will choose the minimum one among these, which is this one. All right. So at each step, find the edge of the least weighted joining a vertex that is already in T with a vertex not in T and add that edge to T. So now from here, it's just we know that. So at each step, find the edge. Okay, so we did it. Least weight is joining a vertex that is already in T. Okay, so we add this one. We added this one to this vertex. This vertex was already in T. Then we will repeat until we will cover all of the vertices. So now here 7, I can't do that. All right. So because I can't do that because this vertex is already in T. So among this one, 20, 16, 15, 25, I will choose this one. Okay, so among this one, I can't choose this one because this is already in the tree. This one, 25, 25, 22, 13. So I will choose this one, 13. And the rest, the other one, the last one is this one. Okay. All right. So this is the minimal spanning tree by using Prime's algorithm. All right. So Kruskal algorithm. Okay. I wish I could. Okay. I can use a different color. So Kruskal algorithm. I will list all of the edge and list all of the edge of the G in increasing order. So if I list all of that, 5, 6, 7, and the rest, I don't need to repeat. So start the tree by the first two edges. Okay, can I do it? So 16, 6 and 5. So 5, 6. Okay. What's the rest of the story? For the next edge in the list, it forms a cycle with the edges already in the tree. Omit it, otherwise insert it into tree. So we really need to write everything. 5, 6, 7, then what else do we have? We can't choose this one because if we add, it will be a cycle. Then we got 13, 13. Then we got 15. What else do we have? 16, 19, 22, and 25, 25. So, can I choose? So do we choose this one, not this one? We need to choose this one actually. We need to choose this one. It doesn't make. And 15 can choose. Oh yeah, so for connection, we need to choose it really. Okay. 16, we don't need actually. So repeat this. We will repeat this for every edge in the list or until you can see that every vertex is presented. So we should have a condition to say that we already done with all the vertices, or we should analyze all of them. All right. So we see that this like the color has been like compatible with this color. So it means the Prime's algorithm, which for finding minimal spanning tree is the same as the Kruskal's algorithm. It's not the same actually. The result is the same here. All right, let's do this one. Interesting questions now. Okay, so question 18, this one. And we see that prefix order. What's the prefix? Is root. Definitely, this is the root. And left. So root left, so it's the left. Okay, so this one is root left. Right. So now here is the thing. So I should have this one as well. Or just cover these. And I did this one and this one. Now I have this one divide. Again, root. Sorry, I don't have this one. 2 divided. Now I just cover this one here. So it was like root. So this is like a left root and left stuff here and right stuff here. And I'm not sure about this yet. So here is the thing again, is like should be a root of something. So root left, right. So the right stuff is like this plus should be a root itself. And A1 root left, right. Okay, that's all. Yeah, I think this is right now. So infix expression. So can I do that? 2 divided by a plus 1 plus 3 times y. All right. Postfix. I won't do this question 19 because it will be the similar condition. So I can actually cheat from this one. So what's the definition of the postfix? Let's have a look at here. Left, right, root. So I feel that left, right, root. So it should be this guy. So back, this guy should be root. So it comes outside at the last. Now, here is the thing. So you got this, what was it? Left, right, root. So left stuff, right stuff, root. Right stuff, I can. Right stuff. So right stuff is also left, right, root. Now here is this one. So this will be left 2, right, right should be, and then root. So left, right, which we will write it here, right, root, which is this divide. Now this one is this left, right, root. Okay. Now I jump question 19. I can do this one as well. 20. So this one is postfix. So let's remember again. Postfix, left, right, root. Left, right, root. So this one is times A. So I can't go down because minus can't be like here. So it should be here. So root right, left, this should be left. Okay, so let's cover this one here. All right, so this guy here, definitely A, B plus left, right, root, A, B plus B. Then left, then possibly I have left, right. So this will be CD times, so this will be C times D. So left, right, root, left, right, root times. And this will be EF division, left, right, root. So it should be E divide F. So this one should be minus, okay. So because I'm telling that like left, right, root, which is this one here. And let's amend the figure. This guy, this guy. So it comes here and it comes here. Mm. Okay. So now it is easy to fix it now. In fixed expression, there is the usual one. It's like A plus B minus like C times D minus E divided by F. And this one is this big parenthesis minus this one is, did I need it? Yeah, this one should be, yeah, times actually. Yeah, I can amend this one again. Times 8. It will be like this for sure. And that's right. So I just mixed. So I was just confused with this one with the extra minus, but there is no extra minus, so it is times. So left, right, root. Yeah, left, right, root. Yeah, actually left, root, right. So which is for the infix. So I leave this prefix for you, but it is okay. It's so once you have the infix or in order one, it is easy to write the prefix and postfix actually. Okay. Now a binary search tree is satisfying is a binary tree. So a tree which vertices are binary numbers 0 and 1. Okay. So for every vertex v, all of the items in the left subtree v must be less than the items stored in v, and all the items in the right subtree must be greater than that. So if I have this one, I see that A is the root, B is the right child, Oh, sorry. Right child, and C is also right child, and that is right. For part A, part B, A is here, C is right, B is left. That is also BST as well. So you wanna see that which one is the each one is not the binary search tree BST. So A is the root, B is the right, and this one is C, which is not. So this is not a BST. So let's see that BST is a binary tree. Okay, so binary is each like just it has just one or two. Okay. All right, so BST's definition was here. We can see that again. They should kind of order the tree in which each vertex has at most two children. If there are two children, they are designated as a left child and a right child. So we have at most, the degree is at most two. Okay, so let's go there just quickly. All right, we are here. So part D is C is the root, B is the left, and A is the left. That is also right. This is also BST as well. BST, BST. All right, let's go to the other question. Now, this question is about the algorithm. So we see that if I write the proof like this, proof, then I have graphic and the following arithmetic graph following BST. Okay. Okay, so graph is this one, set is here, set, I will write a set here, set 3 here. Okay, for graphic one, arithmetic comes first because it's written first. Logic, it is binary, it is like binary tree. Okay, what is that? Logic. Okay, so we want to have the binary search trees has been the property for every vertex v in all items in the left subtree. Must be less than store in V and all the items in the right subtree of V. So we see here, so done, okay. What is the depth? That's okay, so it's just 2. What is it? Where is the smallest item stored? So arithmetic, because it's in the right, the most right one. Largest is the 3. So traversing in BST, I prefer in order because I can order everything alphabetically. Okay. So the answer is this one because it will be in order alphabetically. And I can use to find the algorithm logic. What is logic? So, okay. So X equal logic. So logic is, so let's have a look at the formula. We see that logic, oops, sorry. So let's find the root. Okay. Okay, so it is the root. So now here in the logic, proof logic. So it's lower than, less than proof. So we will go to this side. Okay. So logic, then left child of the here it exists, then to the left child. So since it is less than this one, so it doesn't satisfy. Logic is not bigger than here or the root. So we won't touch this one. So we will come here and then again here we will set here as the root here. So it is the, so is the logic equal to graph? No. So I just don't want to write this one. Description is enough for this one. So again, okay, so we will repeat again here. So logic is equal here, not yet, because logic is not graphic. Then logic is less than graphic. No, so we won't touch this one. Logic bigger than graphic. Yes, so we will go this side. So then we set here as the root. We will come here. So graphic is this here. The root is equal to logic. Yes. So then we will stop. So we will assign x or logic to be root. So root will be, so this root, which is like we set it here, so logic will be found. Okay. So it is possible to amend this formula, to amend, to insert a new one, a new word for here. So I can use the relation. So I can use the relation here and set relation to. So R relation bigger than proof. So it will be, sorry. So set is the proof. Okay. Let's, the proof is the root. Okay. So relation is bigger than proof. No, so I won't do this path. So now here I will see that proof relation is bigger than proof. Yes, we will go here. So then the root will be this guy here, set. Then I will come back here. So is the relation is equal to this word? No. Okay, then we will compare again. Relation is less than this one. Set, yes, we will go to this side. So I won't do this one. I won't go to this side. Okay, is there anything there here? So we will ask this question. If we will go to this one, and if there is nothing here, I will insert relation there. Okay, then we will be fine. So the program can be amended to, instead of finding something, we can insert a word or a value which keeps the order, which preserves the order. Okay, so we can add this relation here. Okay, question 23. Now, so it says that if you wish to insert a list of items into a BST using the previous algorithms, the resulting tree will depend on the order in which you do the insertion. Create two different BSTs by inserting the following data in the orders given. So If I add this one, this part A, it's easy part A. That's why I wanna do E, F, okay. And if I want to do this one, I leave this one to you, but I can do it for you. But then implementation, I leave the implementation to you. D, and actually E, then F here, then for this one A here, then C here, then for F, so you got this one E, G, so E here, definitely, and G here. So this is the answer, obviously. You can do this, obviously. Okay, you can try to know that one. All right, all the best with the upcoming workshop this in the week 7. Good luck.